We learned how to estimate what on Monday? Interval is a confidence interval of what type of parameter? Standard deviation, mean? Hmm? No, we spent like 2 hours talking about it. We found a confidence interval for well, there was a normal distribution if it was on certain cases, right? But what was the parameter we were estimating? The proportion, the population proportion, right? So that one was a little bit easier because you might think you might start with mean first, right? That would be, but we did proportion, right? Mean's going to have something similar, but it's a little bit different, right? There's a formula for finding the standard deviation based on proportion, right? The QN divided by, QP divided by N, right? That was the standard deviation, square root of that, right? There is no way to estimate a standard deviation from a mean, right? So that makes this a little bit more complicated. So we are going to try estimating. Making sure you have out your table. Yes, although there's more on there. So notice we have this z-score table. How much of this packet have we used so far? Just the front page, right? Have I ever told you to look at anything else? Yeah. So we're going to start using the third and fourth page here. And then the fifth page we'll probably learn how to use on like the last week. So we're going to start using the rest of this packet. So now you know why it's a packet and not just the front. You may have been wondering that, right? Because it seemed like the other stuff we weren't using at all. It's pretty late. So we're going to start using that. If we get into it, I hope maybe we can start 7.3, where we're going to be estimating a population standard deviation or variance. It's not really, the reason why we can do both of them is it's very easy. The standard deviation, how do you get the standard deviation from the variance? Right. So if you can estimate the variance, you just say, let me just take the square root of that bad boy, right? And I'm going to get the standard deviation. So it's not really two procedures, right? Once you estimate one, you get the other one. All right. So let's talk about how do we estimate the population mean, right? So again, right, here's the reason why this one's a little bit more complicated is the standard deviation kind of comes up into this, right? So we're going to, again, explain the confidence interval, right? Remember, a confidence interval is just the interval where you're some degree of confident that you're in that spot, right? And we're going to calculate the confidence interval for a mean, right? So this is what you would, this is more of the standard one. I keep going to the height. I collect a random sample of 20 Americans, or let's say 20 American males, just so we don't have to worry about that difference, right? And their mean height is whatever it is, right? Let's say the mean of that group is 5'9", right? Uh, where can I be 95% sure that the actual population mean is, right? And we'll also determine the needed sample size, right, to get within, like if I say I need the mean within a half of an inch, we're going to find out the sample size that we need to get to that arbitrary level of accuracy. So the main goal of this section, right, is to present methods using the sample mean, right, which is X bar, to make an inference about the corresponding population mean, mu, right? Now, do you now see, anyone think it was strange that we use like different symbols for the different types of means, like at the beginning of this class? Because we would always, yeah, the p hat or the p, right? Like at the beginning, you'd be like, okay, it's either a population or a sample, but the procedure for finding the mean was the same, right? But now we're using both at the same time, so it's important to have them, right? You measure, right? You get a sample. We want to use p hat, right? This is easy to get. This is difficult. All right. what do we think the point estimate of mu is going to be? Point estimate is an estimation that's your point. It's not an interval. It's very straightforward here. It's not complicated. Just imagine, all right? I take a sample of 30 people. Their mean height is 5'9". What would you guess if you had no other information the actual height of the population is? 5'9". So symbolically, what are we going to use to estimate mu? Which is X bar, right? Yeah. So that's the point estimate, right? So, and this again works because, as you found out, mean is an unbiased estimator, right? The mean of the sample means is the population mean, right? We'll use a confidence interval around it, and we'll find the necessary sample size. Now, we have two scenarios, right? So this sigma right here is the what measurement? Sigma, what does it represent, class? Everybody. It represents the standard deviation, but which one? Population standard deviation, right? So there are different methods you have to use for when the population standard deviation is not known, and then you use a different one for when it is known. Now, we're going to focus much more on the one where it is not known. Anybody think of why? Go ahead. It is much more common. Let's think about why. What are we trying? We are trying to estimate the population mean. We would only estimate if right, so we don't have it, right? It's too big to measure, right? It's too big to collect all of it. So we are estimating mu because we don't know it, right? If we knew it, what would be the point of doing this? If you don't know mu, what's unlikely that you would somehow randomly know? I don't know the population mean. If I don't know the population mean, how would I know the population standard deviation? What do you mean?
That sounds far-fetched.
Yeah, well, we don't know. This is the much more common scenario, right? Like, if I'm not sure of what the mean size of a screw is, how would I somehow know the mean exactly? Like, I would have a very good idea of what the standard deviation was. You have to imagine that would be strange, right? Does everyone have some intuition for that, right? Population parameters are difficult to know anyways, and you would think that the mean would be the easier one to find, right, than the standard deviation. So we need to have an idea. Are we getting this? Right? Like, you're not going to know this. So this is the much more important example for us, important scenario to example, right? So if you don't have, so we used X bar as our point estimator for our mean. What would be the point estimator for your standard deviation then? Your population standard deviation. Isn't hard. We think about this, right? Yes, it would be, but here's the thing, right? And you guys found this out when you did the homework on 6.3. Standard deviation S is a biased estimator of the population, right? So that means of the population standard deviation. That means that our S's will not be centered around our population standard deviation. This is hard to see, but if you kind of did that, so that leaves a little bit more uncertainty. And we can account for this, right? So to account for this biasness, right, that leaves a little bit more doubt, right? So instead of using, so we've been using the normal distribution. We are going to use something called the t-distribution. It's actually called the student t-distribution. And notice the calculation for t is the same as the calculation for z, except for with what difference? Look at that formula. What's the difference between this formula and the formula that we use for z? Yes, it's using S instead of sigma. So it's using the sample standard deviation instead of the population standard deviation, right? So that's the big difference, right? And we do this because you don't have it, right? So this gives us a different distribution of values. This calculates something like a z-score, but when you calculate a z-score, right, you always have a normal distribution with a mean of 0 and a standard deviation of 1, right? Does that sound familiar? Now, this t-distribute, right, you always get the same distribution, right? And that's why we able to, the z distribution, right, is this page right here. T-distribution doesn't quite work that way. The t-distributions are different depending on your, something called the number of degrees of freedom. The degrees of freedom really mean how many things you can have changed. Anyone heard the term degrees of freedom before? Right? So your finger has 3 degrees of freedom. 1 is at this joint right here, 2, and 3. Right? It has 3 things you can rotate around. Perhaps you've heard a pilot, they talk about your heading, pitch, roll, and yaw, right? For a plane, right? That's 3 degrees of freedom, right? It's kind of complicated, but right, if you have the mean and the standard deviation of data, right? If I have all but one of the pieces of data, the other one has to be a particular number because I know what the mean is, right? And because I know the standard deviation. So for a t-distribution, the number of degrees of freedom in a t-distribution is n minus 1. So if you have 100, your sample has 100 people in it, your degrees of freedom is 99. This is perhaps the easiest formula you're going to use in this class, n minus 1. Now, just like before, we had to find critical values, right? Before, our formula for the margin of error was z alpha over 2. Before, this was your formula, right, everyone? E equals z alpha over 2, where that was your critical value, right? That's how you got it before. Now, the critical value only depended on what I called CL. CL is the, mentioned it many times on Monday. CL stands for, confidence. I like the C part. It is, it's the confidence level, right? Which was either 99%, 95%, right, etc. Now it's going to still depend on that confidence level, but it's also going to depend on the degrees of freedom, right? There is only one Z distribution. There are many different T distributions. They all kind of look the same, but they're different depending on the number of degrees of freedom, right? if you look at the table A3, that is the third page, you should have a table that looks something like this, right? Does everyone have this? So turn to page 3 of your table packet. Right? That will be our T table, and I will teach you how to read that in a little bit, right? You can also use technology. I'll teach you that too. But as you know, right, even though I'm a little bit old school and then I like to use the table. I'm not because I'm like old enough that I actually ever had to, right? Like these graphic calculators have been around, right, since I've been able to use them, right? It just helps you get a sense of what the hell is going on, right? So it's not all magic happening behind the curtain, right? So, but I'll show you how to read that in a little bit, but let me talk a little bit more about the T-score, right? So let me give you some facts. So I want you all to look at this carefully. It might be hard for you to see in the back, right? In the back, can you see several different curves here of different colors? Let me see. What's the color of the curve that's on the top in the middle? Green. So that green curve is the normal distribution. It's at the top on the middle, right? But this is a continuous probability distribution. Bobby, you're good at answering this question. What is the area underneath that curve? 1, right? And these are all probability distributions, which means the area underneath all of them must be 1, right? So if this green curve is higher in the middle, right, and its area is 1, this red curve's a little bit under it, right? The blue curve is even under that, right? So notice it's green, red, blue. But the area underneath all the curves, they're all 1, which means they're all the same areas, right? If this green curve is higher in the middle, what must it be to make up for it on the edge? Well, not significantly less, but at least less. Noticeably less, right? Do we get this? If more, since the area underneath each curve is 1, right? This green curve is taller, right? So it must have more of its area in the middle, less in the tails, right? So these T curves, right, the red and the blue one, have thicker tails. Thicker tails means that your standard deviation is higher, right? Because your data is more spread out, okay? We following so far, right? Thicker tails, more spread out, right? There's a lot of math behind it, but I, again, am not an expert in statistics. I know just enough statistics, probably a little bit more than just enough. Don't know, like you're in good hands, right? But I know enough statistics to teach this course, right? I don't know enough to teach a graduate level course, so I don't understand all the details about it. But the way I think about this is this, right? I told you that S is a biased estimate for sigma, right? That bias means it's not as good of an estimate, right? So there's more of a room for a larger variation than we would expect. So that's what causes the larger tails, all right? Now notice this blue curve is a student t distribution with a sample size of 3. This red one is a sample size of 12. Notice which one has the thicker tail, the sample size of 3 or the sample size of 12? 3, that makes more sense, right? The larger my sample is, the less biased my estimate of the standard deviation should be, right? Imagine I only had a sample size of 1. My standard deviation by definition would be 0, right? It would be a very bad estimate, right? With 2, I'd have a pretty bad estimate too, right? So as n gets larger and larger and larger, your distribution becomes more and more like the normal curve. So the fact that this is not a normal distribution, exactly, it becomes less problematic the larger n is. And you can see that these differences aren't that much. So let me summarize some of the things that I just said here. One thing is, notice now I call normal curve the bell curve, because you probably only heard of one before, but that's not actually accurate. The normal curve is a bell curve. I call it the bell curve, like the Ohio State University, if you ever watch sports. Don't know why they call it that. They did it. My dad used to teach at Ohio State in the 90s. They did not do that then. It's a newer thing. They started doing that in the last 20 years. Yeah. It's always been. All right. So every T curve is a bell curve, right? The normal curve is just the most common bell curve, right? So it's both symmetric and it is much higher in the middle than it is on the edges, right? But for a normal distribution, those edges are a little bit thicker. The T distribution has a mean of 0, but the T distribution, right? This is important, right? The standard deviation, the STD of the T distribution is always greater than 1. How much greater than 1 it is? As T, it is significantly greater than 1 when T is small, when n is small, right? When n is very large, it gets closer and closer to 1, right? Using limit notation, which is like kind of a calculus thing, just thinks as n goes to infinity, T goes to 1, right? And as n goes to infinity, your T distribution becomes more and more like the normal distribution. Yeah. STD. As n goes to infinity. As n gets really large, T gets closer and closer to 1, but never quite reaches 1, because you never can quite have an infinite sample size. Well, because your population size is not going to be infinite either, right? So now let's really focus on that third table. Let's look at how to read it, okay? So hopefully you can, this page isn't the same. So can you guys look at this and see, can you kind of see how this translates to your table? Because it's not quite the same size. Like my table starts here and it ends about halfway, and then it kind of picks up on the other side. All right. So, and then I believe your table also has something that looks like this on there, right? Yeah. So just like before, you have two critical values, and they will have the same absolute value, right? Because the T distribution is symmetric. Just like, is the Z distribution symmetric as well? The Z distribution, the normal distribution, is it symmetric? Yes, absolutely. Right? So this, though, instead of having one big table that explains the whole thing, we just have a couple, since they're infinitely many T distributions, we just have a couple of values from each one, right? So let's say, Bobby, what of 90, 95, and 99, which is your favorite confidence level? All right. So this is a 90 confidence degree level, right? So that means we would have 90% of the area in the middle, right? Okay, which means that 10% would be the area in two tails, and 5% would be the area in each tail, correct? So we want a critical value that separates the middle 90% from the 5% on each edge or the extreme 10%, right? Now, you would look in the intermediate, right? So Bobby's confidence level is 90%, right? So which column do you think corresponds to a confidence level of 90%? Column 1, 2, 3, 4, or 5? Everyone look at your table in front of you. So here, there's 10, but there's two different 10s. So is it the first, second, third, fourth, or fifth column? Which column corresponds to a confidence level of 90%? The fourth one, because area in two tails is 10%, right? Which means the area in one tail or each tail is 5%. Bobby chose a confidence level of 90%, which means, right, this area is 90% or 0.9, which means that you have 0.05 in each tail, which is a total of 10% in two tails. What? Nothing yet. We need to build we need a critical value. We're getting critical values, which will be a formula that we use later, right? So from Monday, when we did for a proportion, we did the z distribution, right? Once I told you the critical value, once I told you the confidence level, that was enough to find the critical value. Today, there's something different. You also need, what's the other piece of information that this table, that these values depend on? It was the confidence level, which is this. What's the other dimension of this chart? So that's the horizontal dimension. What's the vertical dimension of this chart? Correct. Right? That's the other thing it depends on. So when we find our critical value, that is going to depend on the degrees of freedom. Okay. Well, Regina, choose what's your favorite sample size? Sure. Okay, so Gina says n is 30, but we got to be careful. N is 30, but the number of degrees of freedom them everybody is, yeah, so degrees of freedom is 29. So this is the number of degrees of freedom, right? And we found out that earlier, this is our confidence level. So then we look at the chart. There we would get our critical value. So our T critical value, our T alpha over 2, is 1.699. So then we can go back to our picture. This is T equals 1.699. And this is T equals negative 1.699. So that gave us the two critical values that's the how far right and how far left you need to go to cut off the 5% extremes, right? And keep 90% in the middle. Yes? It's not normal. Remember, it's almost normal. Correct. But remember, actually, it's good. I'm glad you said this, right? It looks normal, but it looks a little bit thicker, right? Remember, it is symmetric, though, like a normal distribution, which is why there's symmetry we find here. Where's the picture? So, Regina, this green curve is this standard normal distribution. These curves are very close to it, but not quite, with the differences being more extreme for small values of n, right? So looking in each column, what do you notice as the number of degrees of freedom happens? What happens to the critical values? Like there's a trend. Absolutely. Because it becomes more and more normal the larger n gets, right? The more normal it gets, the less thick those tails are, right? So the more of the area is in the center, right? So the less far out you need to go to get a particular area, right? You can see that, and you can see that at the beginning, right? Increasing a degree of freedom really decrease it, like doesn't make, it makes a huge difference. When you get smaller, right? Notice the values change less each time, right? So let's say, so notice, I mean, you can use your calculator too. I'll show you how to do that. But notice that this table at 40, it stops going up by 1, and then it starts going up by 5, then start going up by 10, then stops going up by 100, then it goes up 500, and then 1,000. Then it just says large, right? So the reason is, right, the difference between having 800 degrees of freedom and 802 is tiny, right? So if you have a very large number of degrees of freedom and the exact number of degrees of freedom is not on this table, just use the thing closest to it. So by 77 degrees, just say I'm going to treat that like it's 80. All right, so let's take a break there, and then we will come back. All right. Well, let's come back together here. So anything new in this slide? No, we used that before. We used that on Monday for the margin of error formula, right? Sample mean, that's new. Well, it's, yeah. They're all there, right? We all know what this means, so we're going to be able to use this, right? So again, when are these confidence level calculations valid? Well, one, right, and this is always the case, right? And this is what I've been saying, right? In real life, it's hard to calculate a simple random sample, right? If you could easily do that, right, you get an A in this class, you could be a professional pollster easily, because you could just use all the formulas here and that would tell you, hey, right, I got this many people in my sample, right? And hey, n's bigger than 30, so this is my margin of error. I'm 95% confidence that the percentage of people that currently support President Biden is whatever percent you have, plus or minus 3%. You could easily do that, right? The problem is in real life, nothing simple random, right? Okay, so to use the calculations for calculating these confidence intervals, right? We want n to be bigger than 30, right? Or you want to know that your original data is normally distributed. Now, we know our original data is normally distributed, yet we still use the t-distribution because we use the t-distribution when what condition occurs? What have we been talking about this whole time? The whole premise is what is not known to us. What? Did you say something? Okay, what is unknown for us to be using what type of standard deviation? Population. You're always going to know the sample standard deviation because you have access to the sample, right? You can just calculate it just like how we learned in chapter 2, right? So that's the whole method, right? That's the whole thing, right? I want you to make that key thing, right? You only use the t-distribution when the standard deviation of the population is unknown. And here's the formula. Notice it's pretty similar to the other formula. So our formula before was E So just like before, before we used Z alpha over 2, here we use T alpha over 2. We have dividing by the square root of n, and then we use a standard deviation as p hat q hat. Here we use the standard deviation. We don't know the standard deviation of the population, so we say, well, our best, but however biased guess is our sample standard deviation. And remember, T alpha is going to depend on 2 things: degrees of freedom and your confidence level. This says here, your critical value is what's separating it off, right? And etc. So let's just do an example of this, all right? We want to find the T critical value using our table. Let's try this together, right? So everyone look at your table, corresponding to a 95% confidence level. So first, let's draw what our curve will kind of look like. Now, that does not look symmetric at all. So here's my T curve. I made the tails much thicker than in the normal curve, but just to give you the idea, okay? And it's symmetric. And Bobby, you said 90%. This one's 95, right? So that 95% is the area in the middle. So 95 is in the middle, which means what's the rest of the area? The rest of the area is 0.05, right? That's the area in 2 tails. What's the area in 1 tail? Would be half of this, right? Right, half. It would be in 1 tail. Right? This is 0.025. This is 0.025. Okay, and the other thing is we're told n is 15. So what does that mean? N is 15. So n being 15 tells us what that we need to know before we go to town on our table. Yes. So degrees of freedom equals 14. Exactly. So let's turn to our table, see if we can figure, I'll turn it here. See if you can find the number on your own quickly, and then I will help correct you, right? See if you can find the critical value. So what column do we use? Third, oh, that's the row. Yes, because that has, right, make sure when you're looking at this that you're not just looking for the value, make sure that you're thinking 2 tails, right? I've even done it myself. And we already did the -1, so I don't need to look in the 13. I'm looking in the 14. 1 second, let me just circle that number. So our T critical value is 2.145. Yes. Correct. Yes. And we won't really be doing that until the next chapter. But like you can do either because you know it's symmetric, right? So like the area in 1 tail determines the area in 2 tails. It's not like it's going to be asymmetrical, right? The area in 2, yes, because it's symmetric, right? And that's why it only gives you 1 critical value, right? Even though strictly speaking, not even strictly, let's see here. We found, already forgot it. What was the number I just gave you? It was something, 0.14. Yeah, 145. So notice 95% of our area is between T equals 1.145 and T equals negative that, again by symmetry. So we found 1 critical value, but there really are 2. It's just the other one's always going to be the negative of that, right? So we found this area. So then this is our 95%, right? They wanted to be a little more conservative than Bobby, right? With his 90. That's how finding the T critical value, which is actually kind of the hardest part. The rest of it is just using a formula. We'll use it and then we'll do the calculator. All right, let's read this problem. Okay. Example 1. A study was conducted to estimate hospital costs for accident victims that wore seatbelts, right? 20 randomly selected cases have a distribution that appears to be bell-shaped with a mean of $9,004 and a standard deviation of $5,629. All right, so let's read some of the information out of here, right? And then also do some other things. Okay, so let's see what we can get out of here, all right? So the first number I see here is 20. So 20 corresponds to what? That equals what? N. So that means there are 20 people in the sample. Now it says, read that rest of that sentence to yourself. I want to point something out, all right? Here are the conditions for using the methods we're going to have. Either N, so here's what it says. Can we use the formula? Are we satisfying these conditions? But N is 20, that's not more than 30. No, you were right, Regina. I was tricking you into thinking you were wrong. Why was she right even though she wasn't sure? So read the prop. So it says N needs to be more than 30, or look at 2 more carefully, or what did my problem say? It said appears to be bell-shaped. So we're going to take that to mean that it's normally distributed, okay? So we're good there, all right? So that's the 20. We're good to go, right? Even though this is true, we're still good to go, right? We can still use it because to be normal. All right, let's see. Either of you in the back corner over there, tell me what this 9,004 is. So that's it right in there. All you have to do is read it. 9,004 corresponds to the, say that again? But what about them? $9,004. That is, what type of mean? Population or sample mean here? Sample. The whole point of this exercise is to estimate the population mean, right? All right, I see one other number here. And what type of standard deviation? Sample, which means we use S as the symbol for it, correct? And do we use a Z or a T distribution? T, because while we have the sample standard deviation, do we have the population standard deviation? No, and it would be weird if we did. Because we're trying to estimate a mean. How would you know, why would you need to estimate a mean if you knew the standard deviation? That would be unusual. Okay, so we have most of this formula set up for us, but we are missing T alpha over 2, which is the critical value. The critical values for T alpha over 2 are in your chart, right? Now, to know them, the critical values depend on 2 different things. Horizontal dimension and the vertical dimension of the chart. So the horizontal dimension of the chart depends on that's the vertical. Oh, yes. And how do we know what that is going to be? Yes. Right. Yes. Well, if we were looking at the one tail part, if we're looking at the 2, you'd use. Let me specify what I mean there, because you're right, but you just have to specify, and I'll show you what you mean. So, right, he was right. So we'll look at that. Degrees of freedom. What's that in this case, everybody? Which is 19. Okay, and then our confidence level, right? That's directly mentioned 99%, right? So that means that we've got 99% in the middle, which means, as she was saying, okay, that means, I think this is what Regina was saying, there's 1% or 0.01 in both tails combined. So in each tail, we'll have 0.005. But you can think about it either way, right? Whether you're a one-tailed for now, right? So when we look at our chart, what did we say was the number of degrees of freedom? Okay, so that's where we look. And then this is what I'm saying. So be careful. So Regina, what column do I look in? It is the first one, right? And this is what I'm saying, right? You can think of this as, right? You would both get it right. Maybe Regina thinks of this as 0.005 in one tail. Maybe Bobby thinks of this as 0.01 in both tails combined, right? As long as you're looking at as long as you have the correct value and you're thinking about the correct aspect, you'll get it correct. So our correct value is right there. Our T alpha over 2, the critical value we need to use is 2.861. So then I just need to change the formula. So this is 2.861. You can throw that into your calculator. You know what you get? I need to remind myself of something myself because it's been a while since I've done this. If you all get the same value, so that will give you your E, right? See if you can use that to find the actual confidence level or confidence interval. Sorry, the confidence level is written right there. So when you guys threw this in your calculator, you should have got approximately 3,601. Did we get that? Now that is our margin of error, so to speak, right? So our confidence level, right? What's our point estimator of our mean? Our population mean? What is the point estimator of our population mean? I have one number. I have to guess for the population mean. What? Yes, being. There's a lot of numbers here. 4. That's our sample mean. So that's what we're going to guess, right? And this is our margin of error, right? So we could say with the confidence level, with the 99% confidence level, we can say that we're 99% sure we are within E, either to the left. This is literally what you do with the margin of error, right? You add it to your best guess, right, to get the low range and the high range, right? So I actually did this earlier. That means I am confident at the 99% level that the mean of hospital costs, well, America, right, for being in an accident while wearing your seatbelt, right? I know that I'm 99% sure that the mean is between $5,403 and $12,605. That's a pretty big range, so perhaps I would want to collect a larger sample, right? Because not a great one, but it could be. But yeah, you're gonna need that for your hospital costs. That's more important. But yeah, no, that would. Okay, so that's how you do it by hand. Let me show you how to do it on the calculator. So if you have your calculator, pull that out. All right, so we turn it on. And then what we're going to do, and we'll learn this menu later, is you're going to hit stat. Remember, we used stat to enter in data into our calculator earlier. Then you're going to scroll over all the way to tests. You're going to scroll down past where it says Z interval to T interval, option A. Hit enter. Now yours probably starting to look like this, right? So this would allow you to do a t-test if instead of having statistics, right? Like here in our particular problem, we had the sample mean and the sample standard deviation. Instead of that, I could have just listed the 12 costs, right? And then you need to put them in each cost into L1, right? But we're not doing it that way right now. So if you have like numbers in a problem, instead of just raw data, you want to scroll over to stats, hit enter, and then you put the appropriate values in there, right? So in this case, X hat was 9,004, right? And then the standard deviation was 5,029, right? N was 20. And the confidence level we wanted was 99. So yes, don't write it in as a percentage. It's going to give you an error, right? This has to be a number between 0 and 1. And then you hit calculate, and there, check it out. That's the interval we just got, right? We said that our mean, we were 99% sure those are the exact same numbers. Now, on the celebration, right? Showing your work is a good idea. Now, I don't strictly require you to show work, but if you accidentally hit, I don't know, make a small mistake, and your calculator just spits out a number. Does everyone see how to read this, right? At the top there, right? This is showing you the lower end of the interval, and that's the upper end, right? Now, when you celebrate on this stuff, it would be good if you're using this just to tell me what you typed in. So you can write T interval, right? You can write this down, T interval, like show me what you typed in your calculator. Then if you get the wrong answer, I can give you partial credit. I'm like, oh, you got 3 of the 4 things right, but you accidentally typed in the wrong confidence level or something like that, right? If you just get a number and I don't know where it came from, it's going to be 0 out of 5 instead of maybe 4 out of 5 or 3 out of 5, right? So that's how we do it. Questions? All right, so you have a 99.5% confidence level. We did 99. See, that'd be a good reason to write your work, right? Because I would just say 0 out of 5, but then that's probably a 3 or a 4 out of 5, right? Okay, so back into I have it here. Okay, what do I do now? Yeah, let's finish this and then we'll get to the end. We'll do one. Okay, so here's the other thing, right? So here, based on my sample size, right, we were able to calculate a margin of error, right? I could ask you to do the opposite. I could say, hey, I need a margin of error for my mean at a 99% confidence level to be a half of an inch. Okay? How big does my sample size have to be for this, all right? So we want to require, we're trying to figure out our sample size. How many people do I need to include in my sample to get a particular level of accuracy? Now, this formula, you end up using the z-distribution. And even though I said all that stuff about standard deviation, why would you know it? You need to know it here. Or at least need to have an estimate for it. Because this is before doing a study. You might not have an estimate of it, right? But you need to do your best you can. So here's the formula you use to calculate. Yeah, go ahead. We've been using these things for a while, right? Yeah. So here is the formula, right? So to calculate the sample size you needed, right? Remember when we did this before, what did I tell you to do with n and rounding? Always up. Yeah, right? Because it's a required sample size. Now, the thing that's weird here is the whole point of collecting this sample is to see how big of a sample, right? It's to calculate the mean. Yeah, you already need to know the standard deviation of the sample before you start. Right? Why would you know it? Well, you wouldn't. So that's kind of a problem. There's some methods you could use to guess, right? So you're probably going to not know sigma. What you could do is before collecting your big sample, right? Collect a smaller sample, right? Do range divided by 4, right? Or look at some earlier study that could give you an estimate of sigma. right? Do a collection process without knowing sigma, collect 20 or so pieces of data, calculate sigma, right? And then that tells you how big your sample needs to be, right? But that's realistically, in this class, I would just give it to you, right? So let's say, assume we want to estimate the mean IQ score for a population of statistics students. How many statistics students must be randomly selected if we want our confidence level to be within 3 IQ points of the population mean? And we're going to assume that the standard deviation is 15 points because that's what it is for the whole country. That the test is designed so that that's the standard deviation. Okay, so first we need to figure out z alpha over 2. So since we're using z and not t, what table should we be looking at? The z table, right? Now, we want 0.95 to be in the center, right? Let's look at our z table again. Now, I quoted you the most common values. You might remember this one. It's 1.6 something, right? I'm close to that. But remember, let's use the z table to do this. So the z table says what? The table values represent, it says it right on the top of your table, table values represent, are we looking at the t table or the z table? Z table. Areas are represented. Table values represent area to the left, right? So we want to find this z-score, right, that cuts off, and the negative value of it that cuts off the center 95% of data. So what is going to be the area to the left, class? Is it going to be 95? No, because what's the area in each tail? Yeah, 0.025. And since we're trying to find the area, we're trying to find this z-score right here. What's the area to the left? Yeah, so 0.975. And is that our z-score or is that the area? Area. So let's look at our, so that is the number in the interior of our table, right? When you're looking for a z-score and you know the area, you want to look at the interior of the table. Okay. Oh, it's a little blurry. So what number should we be looking for in the interior of the table? 0.7. 0.975. And look, where is that number? So that's our z critical value. You added the left tail because notice the values in your table, right? So it says it right on the top of your tables. Represent area to the left. So that's our z critical value. That will always be for 95%. You memorize that value, you don't have to keep finding it. The rest of the information we just plug in. So it's, make sure, notice that there's parentheses around this. You have to multiply. So you have to put parentheses when you type this in your calculator as well. So that's this, sigma. Let me show you me typing that in. Oops, I forgot to put my parentheses. So let's insert them here. Then we have to square it. So I get 96.04. Oh, you can't see any of this. 96.04, but this is a sample size calculation. So the required sample size is actually, Regina told us earlier how to interpret this number. So this is n. N represents everybody. N, sample size. Can I have a sample size of 96.04? Correct. So our required sample size is 97, right? Because you need to, right? We would just be just a tiny bit under 3 points, right? So you have to be conservative, make it bigger, right? So it's really saying, it says n is equal to have the required sample size, n needs to be greater than or equal to, so 97, right? It's people. I could do sample size where I'm measuring trees or whatever, but in this case, it is people, right? So the answer would be 97. So that's how you calculate sample size. You might do that occasionally, but the most important thing is calculating. Let's see here. I don't have it here, so I will write it up there. Has anyone ever heard of the Atkins diet? No one's heard of it. Diet. Okay. It used to be very popular when I was in high school, so it's normal that nobody here has ever heard of it. That's a completely different thing. It's like a dot. Yeah, okay, I'm old. All right. I don't know. I've heard of the Atkins bar. I'm not sure how it's related to the diet, actually. The Atkins diet is like you just eat like protein and you don't, so you just eat like red meat and vegetables and no carbs. This used to be an idea that this was a healthy diet for everybody, but like that's not true. Yeah, I guess that's that. We used to call it the Atkins diet because this guy, Dr. Atkins, came up with it. Then he slipped on the pavement and died. So I don't know what the moral of that story is, but there's got to be some moral there. So in the Atkins diet, right? So it's an old school thing, right? So Atkins diet, right? Atkins diet has 40 adults, all right, and after 12 months, their mean, so these 40 adults' mean weight loss was equal to 2.1 pounds, all right, and their standard deviation was equal to, yes, I know, 4.8 pounds. All right, so I want a confidence, so my confidence level, that's CL, is 90. I want 90% confidence level, right? So I want you to find the CI, that's not confidence level, that's the confidence interval, right? For mu, and you need a confidence interval for mu because this mean weight loss up here, is that mu or is that X bar? Confidence interval. I want you to find the confidence interval at 90%, right? I want you to try to do this by hand, right? So this is like what we just did with the, remember the example with the hospital cost?